So my name is Sanjeev Subragasan, and I'll be looking at the problem set 1, question 2, A and B for ECON3123. So in this problem, it's a multitasking problem where the principal can only incentivize the agent on one task, but here there is a crowding in effect as opposed to a crowding out effect. So the agent's effort in one task reduces the agent's marginal cost of effort in the other task. So in this game, we have one agent, one principal, and the principal's utility is given by x1 plus x2 minus w, where x1 is the output in task 1, and x2 is the output in task 2, and w is the wage paid to the agent by the principal. We have the utility of the agent given by wage minus half e1 squared plus e2 squared minus e1 times e2. We have the wage given by alpha plus beta times y, where y is also equal to x1. So these problems essentially have 4 steps. And we work backwards. So step 4 is where the principal pays the agent wage rather, which is alpha plus beta y. But then we move to step 3, which is where if the agent accepts the wage, he chooses E1 and E2. So E1 and E2 in this case is the agent's best response. So we first set up the agent's maximization problem here. So we have his utility given by W minus half E1 squared plus E2 squared minus E1 times E2. And we already know the value for W, or we know the equation for W, which is A plus beta times E1. Now we get E1 from the fact that y equals x1 and x1 equals e1. So we substitute that in, and then as we're maximizing e1 and e2 in this case, we differentiate the agent's utility with respect to e1 first off, which gives us a beta minus e1 plus e2 over 2, that's equal to 0. Then we differentiate that utility function with respect to e2, which gives us negative e2 plus e1 over 2 equals 0. And we can rearrange that to give us e2 equals e1 over 2. So then we can substitute 2 into 1, and we find that e1 star, which is the best response for the agent for task 1, is 4 over 3 beta, and therefore substituting that back into this equation here, we find that E2 star is given by 2 over 3 beta. So now we know what the agent has chosen as their best response. We can then move on to the principal's maximization problem. So in this case, the principal needs to provide the agent a level of utility which would lead the agent to be indifferent between choosing that utility or his outside option, and therefore we can say that UA, which is the utility of the agent, minus the outside option U0 is equal to 0. And then rearranging that, we know that the utility of the principal will then be given by utility of the principal plus UA minus U0, and we know that to find a socially optimal solution, we are trying to maximize the total utility. So that total utility here is the utility of the principal plus utility agent, which gives us U total. So then our principal's maximization problem is a little bit different to the agents in that here we're trying to maximize total utility. So we have the utility of the principal given by x1 plus x2 minus w, and we're adding that to the utility of the agent, which is what we saw from part A. So moving on, we can then cancel out w's because we have negative w plus positive w, and then we can also substitute x1 and x2. We can substitute e1 and e2 into x1 and x2 respectively. And then we know from part 1, or from part A rather, we know that E1 star is given by 4 over 3b, and E2 star is given by 2 over 3b. So we can then substitute these values into the principal's utility function here, as we're trying to maximize beta in this case, given that this is the variable that the principal can affect or can choose. So substituting in gives us this equation here, and then we can further simplify it, giving us 4 over 3b plus 2 over 3b minus 16 over 18b squared minus 4 over 18b squared plus 8 over 18b squared. Further simplifying that gives us the utility of the principal equals 2b minus 2 over 3b squared. Then, as I said, we are looking to maximize beta. So we make that equal to 0, and differentiating that function gives us 2 minus 4 over 3b. And then rearranging that gives us b star, which is the optimal amount of b in this, optimal beta in this case, which is given by, which is equal to 3 over 2. Now, as I said at the start, this part of part B, the agent needs to be at least indifferent to between choosing his utility and choosing its outside option. So we need alpha to have an amount which creates this level of indifference for the agent. So knowing that, so just going back here, we know that E1 star equals 4 over 3b and E2 star equals 2 over 3b. Now that we know the optimal values of beta rather, we can then substitute them into these equations here, which gives us E1 star equals 2 and E2 star equals 1. And then we are essentially trying to get the level of alpha, which, as I said, makes the agent indifferent. So plugging these into the agent's utility function gives us alpha plus 3 over 2 times 2 minus 1 over 2 times 2 squared plus 1 squared minus 2 times 1. And we find that alpha star equals 3 over 2. So this is the optimal amount of alpha, which will make the agent indifferent between choosing whatever the principal is looking to give them or his outside option.